Welcome to a lesson on surface integrals of a vector field. Let's first talk about oriented surfaces. An oriented surface has two distinct sides with a possible tangent plane at each point on the surface except on the boundaries. So here we see a surface in red with a blue tangent plane. At the point of tangency, there are two possible unit normal vectors, one pointing up, pictured here in blue, and one pointing down, not pictured here. If we use a unit normal vectors pointing up, it gives the surface an upward orientation. If we take a look at this plane here, if we use a unit normal vector n sub 2, it would give this plane a downward orientation. An example of a non-oriented surface would be the Mobius strip, where there's not two sides to the surface. Now let's talk about the surface integral of a vector field. This surface integral is often called the flux integral, and it measures the flow of F across the surface S. It's equal to the double integral of F dotted with N integrated with respect to S, where S is the surface, and N is a unit normal vector field to S. So if our surface is given as a parametric surface, we use this formula here for N, and if the surface is given explicitly, we use this formula here for N. This video will focus on explicit surfaces, so let's take a closer look at this formula here, where big G of x, y, and z equals z minus g of x and y equals 0, n times differential s would give us this quotient here times differential s, where differential s has this Jacobian or integrating factor times dA. So what we'll notice here is this simplifies nicely. This magnitude simplifies out. So n times differential s is just equal to the gradient of big G times differential a. And one more thing to notice before we summarize this, notice that the partial derivative of big G with respect to z would always be 1 if the surface is given in this form. So we often use the following shortcuts to evaluate the surface integral of a vector field given the orientation of the surface. If z is equal to g of x and y, and r is in the xy plane, we can use this double integral over the region R to evaluate the surface integral if it's oriented upward, and we can use this double integral over the region R if the surface is oriented downward. And notice the only difference between these two are the signs of the components as we see here. Let's take a look at our first example. Here we want to determine the flux across the given surface where the vector field is equal to 0, -1, -2, and the surface is z equals 6 minus x minus y. So the first thing we should recognize is that g of x and y is going to be equal to 6 minus x minus y. Now before we set this up, let's take a look at this graphically. You could think of the vector field as representing a rainstorm, and you could think of the surface as the roof of a building. So the surface integral would represent the flow rate of the rain on the roof. So let's go ahead and see what that would be. Notice it says to use a downward orientation, so we'll use this double integral over the region R for our setup. We'll have the double integral over the region R on the xy plane of f, which is angle bracket 0, -1, -2, dotted with angle bracket the partial derivative of g with respect to x, that's going to be -1. The partial derivative of g with respect to y, that'll be -1. And the z component will always be -1 if it's given in this form. And then for differential a, we're going to go ahead and use dy dx. And then in order to determine the limits of integration, we're going to go ahead and sketch the xy trace of our surface. So if z was equal to 0, we could move the x and y terms to the left, and we'd have x plus y equals 6. So we have an x and a y intercept of 6. So for the limits of integration for y, they'll be from 0 all the way to the line. Well, that'll be from 0 all the way to a function of x, so we'll solve this for y, it'll be 6 minus x. And the limits of integration for x will be from 0 to 6. Let's go ahead and determine this dot product. We're going to have 0 plus 1 plus 2, that'll be 3. And from here it'll be pretty straightforward. We'll have 3y. So when y is equal to 6 minus x, we'll have 3 times 6 and 3 times a negative x. That'll be 18 minus 3x. Then when y is 0, we have 0. So we're going to have 18x minus 3 halves x squared. Subbing in 6 for x, we'll have 18 times 6 minus 3 halves times 6 squared, all minus 0. This is going to give us 108 minus 54, which is 54. And again, we can view that value of 54 as the flow rate of the rain on the given roof. I think we'll stop here for this video and take a look at a second example in part 2. I hope you found this helpful. Thank you for watching.